You know, people ask me sometimes, do you think we'll ever travel to the stars? And I always want to say yes, because it's a wonderful idea and the optimism is kind of beautiful. I mean, I appreciate it. But then the physicist in me gets in the way, and the physicist in me starts doing arithmetic. And once you start doing the arithmetic, something very uncomfortable happens. So let me tell you what I mean. The nearest star to us, other than the sun, is a little fellow called Alpha Centauri, and it's about 4 light years away. Now, 4 light years sounds like a distance, but let me tell you what that actually is. Light going as fast as anything in the universe can go takes 4 years to get there. 4 years. Just light. Just pure, massless, fastest thing there is. Light. Now suppose you get in a spaceship. The spaceship with the most fantastically powerful engine you can imagine. And you want to make this trip in, say, a reasonable human lifetime. 20 years, let's say. You want to cruise over to Alpha Centauri and back in 20 years. All right, so you have to go at a big fraction of the speed of light. Maybe 90% of it, maybe more. And here's where the arithmetic starts to bite you. The energy you need, the energy to accelerate something, anything, with mass, to close to the speed of light. I mean, it's not like pushing a car out of a ditch. It grows. It grows faster and faster the closer you get to light speed, and it keeps going up, and it keeps going up, and as you approach the actual speed of light, the energy you'd need approaches, well, infinity. Not a big number, infinity. I remember being in a seminar once, and someone calculated the energy needed to accelerate a spacecraft with a modest payload, a few people and their equipment, up to 90% the speed of light, and then slow it back down again on the other side. The number they got was roughly comparable to all the energy the sun produces in several days. All of it, just for one trip, one way. Now, where are you going to get that energy? I genuinely don't know, and I don't think anybody does. You can't just carry it with you, because the fuel has mass, and then you have to accelerate the fuel too, which needs more fuel, which has more mass, which needs more fuel, and it just spirals on you. This is a real problem. It has a name, actually, the Tsiolkovsky rocket equation, and it is not kind to dreams. But okay, suppose you solve that somehow, you're an optimist. Fine, I'll grant you the energy. Now here's another thing that's kind of curious. Space isn't empty. I know that sounds strange, because we always say space is a vacuum. But it's not a perfect vacuum. There's hydrogen out there. Thin, yes, very thin. But at 90% the speed of light, every little hydrogen atom you run into hits your ship like a cosmic ray. And cosmic rays at that energy, they punch right through metal. They punch right through you, they damage DNA, they cause cancer. And there's no shielding that makes this problem fully go away, because the same thickness of lead that stops radiation also adds mass, which brings us back to the energy problem. So you've got radiation eating your crew alive over years, and you need an almost incomprehensible amount of energy just to go, and then, here's the one that really gets me, you also have to stop. People always talk about the getting there, but you also have to stop. If you're going at 90% light speed and you want to, actually visit the place and not just flash through it and keep going forever into the dark, you have to slow down. And slowing down takes the same energy as speeding up. So now you need twice the impossible energy. Now here is something that I find astonishing, and I mean genuinely astonishing, not just saying that as a figure of speech. If you could somehow do all of this, if you could get your crew up to near light speed, something strange would happen to time. It would genuinely slow down for the people on the ship. Not as a feeling, not psychologically. Actually, really, physically slow down. A trip that takes, say, 1,000 years from Earth's point of view might only feel like, maybe 20 years to the crew. This is real. This is called time dilation, and we have measured it. GPS satellites have to account for it, or they'd give you wrong directions. So in a bizarre way, near light speed travel is actually kind of efficient for the traveler. You age less, time is on your side, but you come back and everybody you ever knew is dead. Your children are dead, their grandchildren are dead. Civilizations may have risen and fallen. You come back to Earth, if Earth is even there, as a stranger from the past. I don't know if that counts as possible in any meaningful sense. The trouble is, when you really look at what the universe allows and what it forbids, you start to sense that there's something almost deliberate about these barriers. Not deliberate, I don't mean that literally, but structural. It's as if the laws of physics are arranged in a way that says each star gets its neighborhood. Each solar system is its own island. You can look across the ocean, but swimming it is another matter entirely. And, I find that simultaneously depressing and wonderful. I mean, it bothers me that I'll never see what's orbiting Alpha Centauri. I genuinely would like to know. But there's something honest and beautiful about the universe being difficult. It doesn't owe us easy answers. It doesn't owe us a shortcut. Now, people sometimes ask about wormholes. about shortcuts through space-time, bending the geometry so 2 points that are far apart are suddenly close together. And I have to be honest with you, we don't know if they exist. We don't know if they can be made. We don't know if they could be stabilized, even in theory. There's some mathematics that doesn't prohibit them, and there's some mathematics that suggests they'd collapse the instant you tried to go through one. What's the real answer? I genuinely don't know. Nobody does. And if someone tells you they do, be a little suspicious. What I can tell you is this. The universe is 400 billion stars in our galaxy alone. And between us and every single one of them is an ocean of physics that we are nowhere near clever enough to cross. At least not yet. And maybe that's the right answer to sit with tonight. Not impossible. Just enormously, profoundly, staggeringly hard. And somewhere out there, maybe something else is sitting in the dark, looking at our little sun, doing the same arithmetic, and coming to the same conclusion. That's the thought I'll leave you with.